In this chapter, we're going to discuss the methodology called logistic regression. Now, logistic regression extends the same ideas as what we saw in the multiple linear regression chapter 6, I believe. But now the target variable is categorical. In chapter 6, in multiple linear regression, the target variable y was an interval variable. I think the example that we saw was Toyota Corolla dataset where the target was the total value of or the price of the cars. Okay, so that would be not a categorical variable but an interval variable. So now in logistic regression we have categorical variable. So we're going to first start with binary target, right? So the target has only two possible values, 0 or 1. And then at the end of the chapter, we will extend that to two cases of non-binary categorical target. Okay, one is if the target is an ordinal categorical variable where the values have an order like 0, 1, 2, 3 and so on. And then we'll also look at a case of nominal categorical variable where the categories are different but they are not ordered. Okay, so we will look at those two special cases at the end of the chapter, but now we're going to look at only binary target. So it's a widely used method, logistic regression, because it follows the very popular multiple linear regression principles. And so it is very good for structured data, meaning that data has some nice features like bell-shaped distribution, not skewed, and not a lot of missing values, and so on and so forth. Now, such familiarity with the methodology among practitioners makes logistics regression a very popular methodology. So we're going to look at the binary target case. Okay, so we start with what is called the logit function. So the logit function is defined in this fashion. So what we want is, okay, so the target is either 0 or 1. So we want to find a function of the predictor variables x's such that the function will give you an estimate for the 0 or 1 of the target. So instead of y as an outcome variable, see we use a function of y called logit, and for the following reason. Let's look at why we define an intermediate function called logit, and from logit we will estimate the probability, which will be the probability of y equal to 1 or 0. Okay. So we start with suppose if we ignore the problems and simply want to use a simple linear regression function like this. So beta sub 0, the intercept, plus linear combination of the predictor variables with the slope coefficients. Okay. Now this value can be used as a probability for class 1 propensity only if we are guaranteed that this value will be a value between 0 and 1. Okay. If otherwise, if this function gives you a negative value, no, negative values are not valid probabilities. At the same time, if this function gives you a result that's greater than 1, again, values greater than 1 are not valid probabilities. So therefore, we must have a guarantee that this function will give you a value between 0 and 1, but that's not the case. Okay, depending upon the values of the x's and the values of the estimates of the slope coefficients, the value of p, the logit function, can be anything, can be anywhere from negative infinity to positive infinity. So the way in which we can handle that is to convert this logistic function, that function, okay, take that function and use it in this formula. So 1 over 1 plus e to the power of minus that function. And when we do that, then we are guaranteed that this value will be between 0 and 1. Okay, so if we use the notation L for that, then the function that we get for P is 1 over 1 plus e to the power of minus L. And this L is called logistic response function, or simply logit function. Now, why would this be guaranteed to be between 0 and 1? So actually, we can show this by plotting the values of all possible values of L and the value of 1 over 1 plus e to the power of minus L. So if we plot the value of L on the x-axis, and we start from a very large negative value, a very large positive value, and on the y-axis we plug in the value of L into this function and plot that, and you see that it is a value. The function will look something like this, the S function, and it's always between 0 and 1. So that's why this transformation from logistic function, with this transformation we are guaranteed to have a value between 0 and 1, which can then be used as our propensity. So how are we going to do this estimation? Now we have to come up with estimations for these beta coefficients. We want the value for b sub 0, b sub 1, and so on, right? And to make that estimation, we cannot use the least squares estimation that we discussed in chapter 6, because the mathematics doesn't work out. But there is an alternative method which is called maximum likelihood. And for that, let's first look at what is the likelihood of a given observation. So you have a given observation, so x, and for that, if we figure out the L function, and we can insert the L value here, and we get the probability of y equal to 1, right? Now if you do 1 minus p sub y, okay, so that will give you a probability of y equal to 0. So this is the probability that y, the class, is equal to 1. This is the probability that the class is equal to 0. Okay. So then, we can see that. So then when you multiply these two functions and form an equation like this, p sub y to the power of y times 1 minus p sub y to the power of 1 minus y, okay, for any given observation, this will give you the probability of whatever the y value may be. So if the y value is 1, then if you plug in that y value into this function, you get p to the power of p sub y to the power of 1. Then this will be 1 minus 1. So this will be, I'm sorry, here this will be 1 minus, so here this will be 1 minus 1, that will be 0. So that part will be equal to 1. So you simply get p sub y. So p sub y to the power of 1, 1 minus p sub y to the power of 0. So you will get p sub y. On the other hand, if y happens to be 0, then plugging in that value in here, so that will be 1. This will be 1 minus p sub y. So this function will give you the likelihood of whatever the value is for that given observation.